Welcome! Today, we'll dive into a fascinating problem from LeetCode, problem number 996, number of Squareful arrays. This problem challenges us to explore mathematical properties of arrays and find efficient solutions. Let's get started. In this problem, we are tasked with finding the number of permutations of an integer array nums that are squareful. A permutation is considered squareful if, for every pair of adjacent elements in the permutation, their sum is a perfect square. For example, numbers like 4, 9, 16, and so on are perfect squares because they are the squares of integers. Since the answer can become very large, we are required to return it modulo 10⁻9 plus 7. The input is a list of integers, and the output is a single integer representing the count of squareful permutations. To understand this better, let's look at the first example. Here, the input array is nums equals 1, 17, 8. We need to evaluate all possible permutations of this array to determine which ones are squareful. For instance, in the permutation 1, 8, 17, the sums of adjacent pairs are 1 plus 8 equals 9 and 8 plus 17 equals 25. Both of these sums are perfect squares, so this permutation is squareful. Similarly, the permutation 17, 8, 1 is also squareful because the sums of adjacent pairs are 25 and 9, which are perfect squares. However, other permutations like 1, 17, 8 fail because one of the sums, 1 plus 17, is not a perfect square. After checking all permutations, only 2 of them are squareful, so the output for this example is 2. The second example involves the input array nums equals 2, 2, 2. Since all the elements are identical, there is only one unique permutation, 2, 2, 2. Here, the sums of adjacent pairs are 2 plus 2 equals 4, which is a perfect square. As there are no other distinct permutations to check, the only squareful permutation is 2, 2, 2, and the output is 1. This example highlights that arrays with identical elements typically have fewer permutations to evaluate, making the computation more straightforward. Now, consider the third example where nums equals 1, 1, 8, 8. This array contains duplicate values, which means there are multiple permutations to check for squarefulness. After evaluating all possible permutations, a total of 18 squareful permutations are found. This example demonstrates the importance of carefully handling duplicate values to ensure that permutations are not overcounted. Additionally, it highlights that larger arrays can lead to a significant increase in the number of permutations to evaluate, making the problem more computationally intensive. When solving this problem, it is important to consider several edge cases. For instance, if the input array has only one element, such as nums equals 1, no adjacent pairs can be formed, so the output is 0. Similarly, when all elements are the same, like nums equals 4, 4, 4, the output depends on whether the sum of two identical elements forms a perfect square. In this case, 4 plus 4 equals 8 is not a perfect square. Another edge case involves handling very large values in the array, where sums can become substantial but must still be checked for squarefulness. Lastly, arrays with duplicate elements require careful consideration to avoid overcounting permutations, ensuring the result is both accurate and efficient. To tackle the problem of generating squareful arrays, we first considered a brute force approach. The intuition here is quite straightforward: generate all possible permutations of the array nums and check if each permutation satisfies the condition of being squareful. To implement this, we can use a backtracking algorithm to systematically generate all permutations. For each permutation, we then verify if the sum of every pair of adjacent elements is a perfect square. However, the complexity of this approach quickly becomes unmanageable. Since generating all permutations has a time complexity of O(n), and checking each permutation takes O(n), the overall complexity is O(n). (n). This rapid growth makes it infeasible for larger arrays. Instead, we can turn to an optimized approach that combines backtracking with pruning invalid paths early. The key insight here is to construct squareful arrays step by step, only continuing down paths that satisfy the problem's constraints. This avoids the inefficiency of generating all possible permutations. Additionally, we can pre-compute the pairs of numbers whose sums are perfect squares, which helps us quickly validate potential pairs during the process. By leveraging these optimizations, we significantly reduce redundant computations and focus only on valid solutions. Building on the optimized strategy, we can further refine the process by addressing duplicate permutations and reducing unnecessary work. Specifically, when constructing permutations, we avoid duplicate results by ensuring that we skip over numbers that are the same as a previously processed number. This prevents redundant computations caused by repeated numbers in the input array. A frequency map is also essential, as it tracks how many times each number in nums can still be used. This helps us manage counts effectively and ensures correctness. The time complexity of this approach is much better than brute force because of the pruning. While the worst-case complexity is still O(n), the actual runtime is significantly faster in practice due to the frequency map and the early elimination of invalid paths. As an alternative, a dynamic programming approach could also be considered. Here, the idea is to use states that represent the current number, the used elements, and the constructed path. For example, a DP state DP, mask, previous, would track the set of used numbers and the last number added. Transitions occur by adding valid numbers that form squareful pairs with the previous number. However, this approach has an exponential state space with a complexity of O(2 to the power of n*n squared. While it may be slightly better in certain cases, its implementation is far more complex and harder to debug compared to backtracking. Among the different approaches considered, we ultimately chose the optimized backtracking approach with pruning. This method strikes the right balance between intuition and efficiency. Unlike the dynamic programming approach, which involves managing complex state transitions and memory overhead, backtracking is cleaner and more straightforward to implement. Pre-computing valid pairs of numbers whose sums are perfect squares helps minimize checks during the recursion, and using a frequency map ensures that duplicates are handled correctly without redundant computations. These optimizations allow us to prune invalid paths early, significantly improving runtime efficiency. While the dynamic programming approach might theoretically offer better performance for certain inputs, its added complexity makes it less appealing for this problem. The chosen strategy is therefore not only efficient but also easier to understand and implement. Key insights include the importance of pre-computing valid pairs, leveraging frequency maps for duplicate handling, and aggressively pruning invalid paths to keep the recursion tree manageable. Finally, let's summarize the complexity of the chosen approach. In the worst case, the time complexity is O(n), which arises from generating permutations with backtracking. However, because of pruning and optimizations like the frequency map, the practical performance is much faster. The space complexity is O(n)² for storing the pre-computed valid pairs and O(n) for tracking the backtracking state. These trade-offs make this approach an ideal balance of efficiency, simplicity, and scalability. By focusing on valid paths, pre-computing necessary information, and avoiding redundant work, this method efficiently solves the problem while remaining straightforward to implement. Overall, it provides a robust and practical solution to generating squareful arrays. In this problem, we aim to generate all permutations of an integer array nums such that every pair of adjacent elements in the permutation has a sum that is a perfect square. A perfect square is simply a number that can be expressed as the square of an integer, like 1, 4, 9, and so on. To achieve this, we follow a systematic approach. First, the input is an integer array nums of size n, and the desired output is a list of permutations that satisfy the squaresum condition. To generate these permutations, we employ a backtracking algorithm. This technique helps us explore all the possible arrangements of the numbers by building permutations step by step and undoing choices whenever they lead to invalid results. Backtracking is particularly suitable here because it avoids redundant computations by pruning branches of the search space that cannot yield valid solutions. Once we start generating permutations, we need to ensure that each candidate permutation satisfies the squaresum condition. This involves checking whether the sum of every pair of adjacent elements is a perfect square. To efficiently verify if a number s is a perfect square, we compute its integer square root using sqrt, s, and check if the square of that value equals s. Additionally, as we build permutations, we can avoid wasting time on invalid ones by checking this condition incrementally. For example, if adding two consecutive elements violates the squaresum condition, we immediately backtrack, pruning that branch of the search. This early pruning drastically reduces the number of permutations we need to explore. Furthermore, if the input array nums contains duplicate elements, we must prevent generating duplicate permutations. Sorting nums and using a visited set or skipping duplicates during backtracking ensures that we only generate unique arrangements. Now, let's dive into some key insights about the algorithm. First, the time complexity of generating all permutations is O(n), where n is the size of the input array. For each permutation, we also need to check the squaresome condition, which adds O(n) operations. Hence, the overall time complexity is O(n). *n. To optimize this, we use pruning to avoid exploring invalid permutations. By verifying the squaresome condition incrementally during the backtracking process, we reduce the number of recursive calls, improving the algorithm's efficiency. Another crucial optimization is handling duplicates in the input array. By sorting nums, duplicate elements are grouped together, allowing us to skip consecutive duplicates during backtracking. This helps prevent redundant work and ensures that the output contains only unique permutations. To implement this algorithm efficiently, we rely on two key data structures. First, the backtracking framework itself is implemented as a recursive function. This function maintains a path variable to store the current permutation being built and a visited Boolean array to track which elements of nums have already been used. The recursion's base case occurs when the path contains all elements of nums, at which point we check whether the squaresome condition is satisfied. Second, we use a set to store all possible perfect squares up to the maximum sum of two elements in nums. This allows us to check whether a sum is a perfect square in constant time, O(1). Pre-computing these perfect squares helps make the algorithm more efficient by eliminating the need to compute square roots repeatedly during the backtracking process. Let's walk through an example to see the algorithm in action. Suppose the input array is nums equals 1, 17, 8. First, we sort the array to 1, 8, 17, and pre-compute the perfect squares, which include values like 1, 4, 9, 16, 25, and so on. We then initialize the backtracking process with an empty path and a visited array set to false, false, false. Starting with the first element, we add 1 to the path, then try adding 8, resulting in path equals 1, 8. We check the sum of 1 and 8, which is 9, a valid perfect square. Next, we add 17 to the path, making it 1, 8, 17. The sum of 8 and 17 is 25, another perfect square. Since the path now contains all elements, it is a valid permutation. We then backtrack and try other combinations, such as starting with 8 or 17, while pruning invalid branches where the squaresome condition is violated. Finally, the output for the input nums equals 1, 17, 8 is the list of valid permutations 1, 8, 17, 8, 1, 17, 17, 8, 1. These permutations satisfy the condition that the sum of every pair of adjacent elements is a perfect square. By leveraging backtracking, pruning invalid branches, handling duplicates, and pre-computing perfect squares, we are able to efficiently generate all squareful permutations of the input array. This solution implements a backtracking algorithm to count the number of permutations of the input array nums such that the sum of every pair of adjacent elements is a perfect square. Let's break it down step by step. 1. Helper function is _perfect_square. This function checks if a given number x is a perfect square. It computes the integer square root of x and verifies whether squaring it gives back x. This is an efficient way to avoid floating point inaccuracies. 2. Main function, number squareful perms. We initialize a counter for the elements of nums using the counter class from collections. This helps efficiently manage the frequency of each number during the recursive backtracking. The self.result variable is used to store the total count of valid permutations. 3. Backtracking function, backtrack. The function takes two arguments, path, the current permutation being built, and counter, which keeps track of the remaining occurrences of each number. If the length of path equals the length of nums, it means a valid permutation is complete, and we increment self.result. Otherwise, we iterate through the numbers in counter. If a number's count is positive, we check whether appending it to path results in a squaresome condition with the previous number, if path is not empty. If the condition is satisfied, we recursively call backtrack with the updated path and counter. After the recursive call, we restore the count of the current number, effectively undoing the choice for the next iteration. 4. Return statement. Once the backtracking completes, the function returns self.result, which holds the total number of valid Squareful permutations. This approach ensures that all permutations are considered while avoiding duplicates by leveraging the frequency counter. The complexity is primarily determined by the factorial growth of permutations, making it suitable only for relatively small input sizes, as constrained by the problem statement. Here, we begin the implementation of the solution in Java. First, we import the necessary libraries, including java.util, which will give us access to data structures like hashmap and ArrayList. Within the solution class, we declare a private integer variable called result to keep track of the total number of valid Squareful permutations. The main function, number Squareful perms, takes an integer array nums as input. We start by creating a hash map called counter to count the frequency of each unique number in the array. This map helps us manage the remaining elements we can use while constructing permutations. After initializing result to 0, we call the helper method backtrack, passing an empty list as the current path, the counter map, and the target length, which is the size of the input array. The backtrack function is where the recursive exploration occurs. If the current path size matches the target length, we have found a valid permutation, so we increment the result and return. Within the loop, we iterate through all keys in the counter map, checking if a number is still available. If it is, we then verify whether adding it to the current path results in a perfect square sum with the last element of the path. If this condition is satisfied, we proceed by adding the number to the path and decrementing its count in the map to mark it as used. Next, we dive deeper into the recursive mechanism. After modifying the path and counter to reflect our choice, we call the backtrack method again to explore further possibilities. This recursive call allows us to build the path step by step. Once the recursive exploration concludes, we undo our choice by removing the last number from the path and restoring its count in the counter map. This backtracking process ensures that we can explore other permutations involving the same number later. The helper method isPerfectSquare is used to determine whether the sum of two numbers is a perfect square. It takes an integer x as input, calculates its square root, and checks if squaring the integer part of the root gives back the original number. This check is critical for ensuring that the array satisfies the Squareful condition at every step. By combining these recursive and mathematical components, the solution efficiently explores all valid permutations while skipping invalid ones. Here, we start with the first example where the input array is nums equals 1, 17, 8. Initially, we set up a counter to track the frequency of each number, resulting in counter 1, 1, 17, 1, 8, 1. We also initialize self.result to 0, which will keep track of the number of valid Squareful arrays. The backtracking process begins with an empty path and the counter. First, we try adding the number 1 to the path, decrementing its count in the counter. This leads to a recursive call with the updated path, 1, and counter. From here, we consider the remaining numbers. When we try 17, the sum 1 plus 17 is 18, which is not a perfect square, so we skip it. Then, we try 8, and since 1 plus 8 equals 9, a perfect square, we add 8 to the path, update the counter, and make another recursive call. Now, the path is 1, 8, and the counter reflects that 8 has been used, leaving counter 1 o'clock, 17, 1, 8 o'clock. Here, we try adding 17 to the path, and since 8 plus 17 equals 25, a perfect square, we proceed by adding 17 to the path and decrement its count in the counter. This results in a recursive call with the full path, 1, 8, 17, and all numbers used. At this point, since the path length matches the length of the input array, we have found a valid Squareful array. We increment self.result to 1, indicating one valid permutation is found. Afterward, we backtrack by removing 17 and restoring its count, allowing us to explore other combinations. The intermediate result here is one valid permutation, 1, 8, 17, and the final output for this example is one valid Squareful array. In the second example, the input array is nums equals 2, 2, 2. The counter now reflects that all elements are the same, with counter 2, 3. We reset self.result to 0. Starting with an empty path on the counter, we try adding the number 2 to the path, decrementing its count. This leads to a recursive call with the path 2 and counter updated to counter 2 2. From here, we again try adding 2 to the path. Since the sum 2 plus 2 equals 4, a perfect square, we add 2 to the path, further decrement the counter, and make another recursive call. Continuing from the path 2 2, with the counter now at counter 2 1, we try adding the last remaining 2. The sum 2 plus 2 equals 4, which is a perfect square, so we add 2 to the path, decrement the counter again, and make a recursive call with the complete path 2 2 2. At this point, the path length matches the input array length, so we increment self.result to 1, marking one valid Squareful array. Afterward, we backtrack by removing the last 2 and restoring its count in the counter. The intermediate result here is one valid permutation, 2 2 2. The final output for this example is also one valid Squareful array. In the third example, the input array is nums equals 4 9 0. The counter now tracks the frequency of each element as counter, 4 1 9 1 0 1. We reset self.result to 0. Beginning with an empty path on the counter, we first add 4 to the path, decrement its count, and make a recursive call with the updated path 4 and counter. From here, we examine the remaining numbers. Trying 9, the sum 4 plus 9 equals 13, which is not a perfect square, so we skip it. Then, we try 0, and since 4 plus 0 equals 4, a perfect square, we add 0 to the path, update the counter, and make a recursive call. With the path now 4 0 and the counter showing counter for a clock 9 1 0 0, we try adding 9 to the path. The sum 0 plus 9 equals 9, a perfect square, so we add 9 to the path, decrement its count in the counter, and make a recursive call with the full path 4 0 9. At this point, the path length matches the input array length, so we increment self.result to 1, marking one valid Squareful array. After backtracking to explore other possibilities, the final output for this example is also one valid Squareful array. To summarize, each of the three examples resulted in exactly one valid Squareful permutation, demonstrating that the backtracking algorithm effectively explores all paths while ensuring that every pair of adjacent numbers forms a perfect square. In terms of time complexity, the solution hinges on a backtracking algorithm, which generates permutations of the input array. Now, if the array contains n elements, the total number of permutations in the worst case is n. However, when duplicates are present, the algorithm intelligently avoids revisiting duplicate permutations by leveraging a frequency counter. This effectively reduces the total number of unique permutations, which can be expressed as n /f_1 *f_2 *f_k, where f_1, f_2, f_k represent the frequencies of distinct elements in the array. This pruning mechanism plays a crucial role in keeping the computational workload manageable, even when duplicates exist in the input. Building on the permutations, the backtracking traversal itself has additional computational steps. For each valid permutation, the algorithm constructs the sequence recursively. At each step, it iterates over all possible numbers, which takes k time, with k being the count of distinct elements in the array. Now, one key operation here is checking if the sum of two elements forms a perfect square. This is handled by the is_perfect_square function, which computes the integer square root in log x time, where x is the sum. Since the sum is bounded by the largest possible value of two elements, this check is effectively constant time, or O1. Each recursive call adds only a small, constant overhead, so the overall cost of backtracking is proportional to the number of permutations. Combining these factors, the overall time complexity in the worst case is approximately O(n). And while duplicates reduce the total number of permutations, the worst case scenario remains dominated by O(n). Now let's analyze the space complexity. The first component to consider is the recursive call stack. The maximum depth of recursion is equal to the length of the array, which is n, as the algorithm builds the permutations step by step. At each level, the algorithm maintains a path array that tracks the current sequence, and this requires O(n) space. Additionally, the counter dictionary, which keeps track of element frequencies, requires O(k) space, where k is the number of unique elements in the array. Combining these, the space required by the recursion stack is proportional to O(n). Furthermore, the auxiliary data structures like the counter object also take O(k) space. When we combine both, the total space complexity becomes O(n plus k). In the worst case, where all elements are distinct, k equals n, so the space complexity simplifies to O(n). To put things into perspective, let's compare this backtracking approach with a brute force method. A naive solution would generate all permutations of the array, which takes O(n) time, and then validate each permutation to determine if it is squareful. Checking the validity of a single permutation involves O(n) work, leading to a total time complexity of O(n). *n. The backtracking approach, however, significantly optimizes this by pruning invalid branches early. Instead of generating and checking every permutation, it builds only those sequences that are valid, skipping unnecessary computations. This makes backtracking far more efficient than brute force, particularly when the input size is large or when there are many invalid permutations. Finally, let's solidify our understanding of the time and space complexities with a formal proof. The time complexity of the backtracking algorithm is dominated by the generation of unique permutations, which is O(n). This holds true because each recursive call performs constant work, and the pruning mechanism avoids redundant computations caused by duplicates. On the space side, the complexity is linear, or O(n), due to the recursion stack and auxiliary data that grow proportionally with the input size. Now, considering different cases, the best-case scenario occurs when all elements in the array are identical, resulting in just one unique permutation. Here, both time and space complexities reduce to O(n). In the average case, with some duplicates, the time complexity lies between O(n) and O(n)f_f_1 *f_2 depending on the frequency of duplicates. In the worst case, with all elements distinct, the algorithm generates all n permutations, leading to O(n) time complexity and O(n) space complexity. This provides a comprehensive view of the algorithm's efficiency across varying input scenarios. One common mistake when solving the number of squareful arrays problem is not accounting for duplicates in the input array. If your algorithm doesn't handle duplicates correctly, it can overcount valid permutations, leading to incorrect results. To fix this, you can use a frequency map to track how many times each number appears, or you can sort the array and skip over duplicate elements during the backtracking process. Another mistake is skipping valid permutations due to incorrect backtracking logic. This often happens when the recursion terminates prematurely or when the search space is pruned improperly. To address this, make sure your backtracking explores all valid paths while adhering to the constraints. Lastly, inefficient calculation of squareful numbers can slow down your solution significantly. Repeatedly checking if a sum is a perfect square during the backtracking process can result in redundant computations. Instead, you should pre-compute all possible perfect square sums for the given elements, which will make the checks much faster during recursion. Another important variation to consider is ignoring constraints on the array size. For larger arrays, such as when n is greater than 10, using a brute force approach to generate all permutations is computationally expensive and impractical. To handle this, you can apply pruning techniques to reduce the search space and use memoization to store intermediate results, which can significantly improve efficiency. Additionally, not validating edge cases is a common oversight. Examples include failing to account for an empty array, arrays with all identical elements, or arrays that don't have any valid squareful permutations. These cases can lead to incorrect outputs if not handled explicitly. To prevent this, test your algorithm with edge cases like n equals 0, n equals 1, and arrays that cannot form valid solutions. Robust edge case handling ensures that your implementation is both complete and reliable. In interviews, understanding the problem requirements is crucial. Specifically, focus on the mathematical properties of perfect squares and how to translate these abstract conditions into actionable constraints within your algorithm. This demonstrates a strong grasp of the problem. Another key point is to optimize early. If the array size allows for techniques like pruning or memoization, discuss these optimizations before jumping into the code. Doing this shows that you're thinking critically about both correctness and efficiency. Clear communication is also essential. When working on backtracking problems, explain your recursive logic step by step, including the base cases and how you handle constraints like duplicates. Finally, be prepared to analyze the time complexity of your approach. For instance, while a brute force solution might take factorial time due to permutations, optimizations can reduce this significantly, and you should be ready to explain these improvements. Related problems like permutations too, combination sum, and subsets can also provide valuable insights into tackling this challenge. There are also alternative approaches to solving this problem. One option is optimized backtracking with a frequency map. This method uses slightly more memory, but it avoids redundant computations by efficiently managing duplicates. Another approach is dynamic programming in a top-down manner. While this can be more complicated to implement, it is highly efficient for larger inputs because it stores intermediate results, reducing redundant calculations. Lastly, you can consider a graph-based approach. Here, the numbers are treated as nodes, and valid transitions, where the sum of two numbers forms a perfect square, are treated as edges. The goal is to find all Hamiltonian paths in this graph. Although this method can be harder to implement, it offers an interesting conceptual perspective and showcases your versatility as a problem solver. Each of these alternatives comes with trade-offs, so it's important to choose the right one based on the problem's constraints and requirements. Great job! Today, we explored the number of Squareful arrays problem and learned how to combine permutations with mathematical insights. Remember, practicing such problems builds your algorithmic thinking. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!